Alright boys, let's talk about muscular gearing. So this is probably going to be my most complex video to date, as muscular gearing is a graduate level biomechanics topic. But yeah, also like no videos on the internet that talk about this, so learning this was quite difficult, but I'll try to break down everything that I know for you guys. Before we go into that, we need to dive into some muscle architecture. So there's two types of muscles, fusiform and pennate muscles. Fusiform muscles basically have their fibers directly aligned in line with the tendon, which is the line of pull. Pennate muscles have the fibers arranged at an angle relative to the central tendon, and they produce force by rotating. Now, in pennate muscles, because fibers are oriented at an angle relative to the central tendon, the muscle is basically able to pack more fibers in a pennate muscle, and this allows pennate muscles to produce more force than fusiform ones. Now, when a muscle produces force, the actual effective force that is being transmitted is the force that is oriented relative to the same direction as the central tendon. What this means is that in fusiform muscles, because the fibers are parallel with the tendon, all the force that the fiber produces will actually perform a meaningful muscle contraction. Now in pennate muscles though, because the fibers are oriented at an angle to the tendon, not all of the force that the fiber produces is vertically oriented relative to the tendon. For example, if the pennation angle of a muscle is 60 degrees and the fiber is producing like 5 newtons of force, only 2.5 newtons of those force are actually being utilized in that contraction. However, because the pennate muscle has so many more fibers due to the muscle architecture, despite the fact that each individual fiber is effectively producing less force, the sheer more amount of fibers allows the muscle to produce larger amounts of force. What this means, though, is that all force that is being produced in a fusiform muscle is going to contribute to fascicle shortening, which optimizes fusiform muscles for better contraction velocity and ranges of motion, whereas the pennate muscles are optimized for force output. I'll break this down more logically for you guys. If you guys look at the biceps are a fusiform muscle. If we compare them to the quads are a pennate muscle. If you notice, your bicep has a lot more range of motion than your quadriceps do, but your quads are just a much bigger muscle because they house so many more fibers. Also, you can physically contract your bicep faster than you can physically contract your quads. Now it gets a little more confusing, but I'll try to simplify everything. If you take a pennate muscle and you put that muscle through a slow but high force movement, here's what's going to happen. And because smaller pennation angles mean more of the force produced by the fiber will be effectively transmitted along the tendon, lower pennation angles will optimize a muscle for force production. In exercises where we're trying to optimize contraction velocity and not necessarily force production, muscles will also operate with smaller pennation angles as well. This is because the fascicles are rotating to produce force, and when the pennation angle is smaller, the majority of the force is going to be transmitted along the tendon, and this can improve fascicular shortening velocity. For example, the hamstrings during sprinting. Hamstrings need to be able to dynamically contract and lengthen, not necessarily by producing lots of force, but it just needs to go through the motion as physically fast as possible so it can get the body in a position to produce lots of force in the swing phase. Preparation from the swing phase into the stance phase. Muscles will operate with higher pennation angles when it is a fast contraction velocity movement, but they're also trying to maximize force. For example, on ground contacting sprinting, the gastrocnemius will utilize higher pennation angles because it doesn't have a lot of time to produce force on the ground, because the contraction velocity is fast, but it needs to optimize force production because it is one of the main propulsive elements of a sprint. This may seem counterintuitive because having a higher pennation angle means that less of the force is being transmitted, but here's why it actually is useful. Because less of the force is being transmitted, what this means is that the fascicles can actually shorten less than they normally would if it was a higher or a lower pennation angle. The fascicles are changing in length less because of less efficient force transmission. What this means is that they are able to stay closer to isometric. And as we know, according to the force velocity curve, force production drops significantly with faster contraction velocities because of the decreased efficiency of cross cycling. Because the change in joint length has to come from somewhere, what this less change in fascicle length is going to do is increase the amount of force that the tendon is able to absorb. This is crucial for producing high amounts of force at fast contraction velocities because tendons are able to rapidly stretch and recoil and return elastic potential energy. We're getting a double whammy with this. What we're getting is more force absorption from the tendon, and we're also getting the muscles able to produce more force isometrically. If you've watched any of my old videos, you know that this sounds a lot similar to tendon and muscle stiffness. If a muscle is stiff, what this allows it to do is have the tendon stretch more with the muscle remaining relatively isometric. So it's the same topic, and they actually go hand in hand here. If If a muscle isn't stiff, it's not able to take advantage of the high gear ratio because it's not going to allow the fascicles to remain relatively isometric and allow the tendon to stretch maximally. Also, the architectural gear ratio is defined as the shortening of the whole musculotendinous unit divided by the fiber shortening. So if you're able to have more shortening of the tendon and less shortening of the fiber, that's a higher gear ratio. Back on topic, right? In order for a muscle to operate with a gear ratio efficiently, we need stiffness. Stiffness is kind of an ambiguous term, and what really makes a muscle have high stiffness? Well, it's activation, specifically pre-activation. For example, if you're doing pogos and you are literally firing your calves before ground contact, your calves are going to resist lengthening, and that lengthening is going to be taken up by the tendon. Whereas if you just strike the ground with a floppy foot in a pogo, you're not going to be able to store as much energy elastically, and you can check this out. You can test your RSI by attacking the ground and letting the ground hit you. You will have a worse RSI the second time because less pre-activation means less stiffness. As we know, a great way to train muscle stiffness is through plyometrics, but it's important to have intent in your plyometrics because if you are not firing your muscles as hard as you physically can, even before they're actually on the ground, then you won't be taking advantage of the main benefit of the plyometric stimulus. How can we improve a muscle's gear ratio? To improve the gear ratio of a muscle, the muscle has to be able to operate with higher pronation angles. The way we achieve this is actually with hypertrophy. Hypertrophy is the addition of fibrils. If you look at a pennate muscle, there oftentimes is not enough room for more fibrils. And the way that the muscle actually accommodates the increased fibrils is by creating space by actually increasing the resting pennation angle. So basically, hypertrophy increases pennation angle and increases the maximum pennation angle the muscle can operate with during fast contraction velocities that require high force. Also mean more muscle force production during the sprint as well. Because even though the pennation angle is slightly higher and thus the effective transmitted force is a little bit worse, more fibrils times a little bit worse force transmission is still going to be more concentric force production. Hypertrophy can also improve muscle stiffness as well because, like I said, stiffness is activation, but more specifically than activation, it's cross bridges. Hypertrophy means more cross bridges, so you get better stiffness. The next adaptation we're going to talk about is how fascicle length and sarcomeres in series affect muscular gearing. Also, one interesting I've noticed is that pennate muscles tend to be on the descending limb and benefit from sarcomerogenesis in series, whereas most fusiform muscles like triceps and biceps don't really benefit from stretch mediation because they're not on the descending limb. And I think this makes sense when you think about it, but off topic. Anyways, an increase in fascicle length is going to be an increase in the number of sarcomeres in a series, which basically means that the fiber or fascicle is getting longer. What this is going to do is it's actually going to increase the maximum shortening velocity of a fiber because there are more fibers or more sarcomeres to perform the individual shortening. So if you pay attention, what the increase in fascicle length sounds like is similar to the benefits of higher operating pennation angles, is that you get a faster maximum shortening fascicle velocity. So here's the thing, right? When you perform exercise at really fast contraction velocities, what you'll notice is that the muscle will literally start bulging out of your body. And this is because the pennation angle is higher, which causes the fibers to literally bulge out of the muscle. The muscle belly can only be so large, right? If you have longer fascicles, they can't operate at higher pennation angles because it will bulge out farther than it physically can. So in this sense, a longer fascicle length kind of limits the pennation angle that a muscle fiber can operate with. I still think you should optimize a muscle's fascicle length. It provides benefits of range of motion, resistant to fatigue at longer lengths. Overall, it's a great adaptation to have. But it's also important that you get your fair share of hypertrophy. In a sense, the benefits might offset each other, but then you get the net benefit of increased range of motion, improved force production at longer lengths, and more force production in general because you have more fibrils, and better muscle stiffness. Yeah, this is the first comprehensive video of muscular gearing on the internet anywhere. And I'm glad I could be the one to share it with you boys.